All right, I want you to do something for me right now. I want you to sit still for just a moment and feel time passing. Go on, feel it. You can feel it moving, can't you? It feels like it's flowing like a river, always going forward, always pushing you from the past into the future. You were born, then you were a child, then you grew up, and right now, right this second, you are moving forward in time. You are absolutely sure of this. You'd bet your life on it. And that is exactly the problem. Because I'm going to show you, not with philosophy, not with poetry, not with some spiritual mumbo-jumbo, but with cold, hard, beautiful physics, that time is not moving forward. In fact, the fundamental laws of the universe, the deepest equations we have ever written, the most tested, most precise, most experimentally verified rules of reality, they don't show time moving forward at all. They don't even care which direction time goes. What you feel as time flowing forward, it's an illusion, a spectacular, convincing, deeply personal illusion, but an illusion nonetheless. And today, I'm going to prove it to you. The universe doesn't have a clock. You know what I love about physics? It has this absolutely marvelous habit of telling you that everything you thought you knew, everything that feels completely obvious, completely self-evident, completely beyond question is wrong. Not a little bit wrong. Not slightly off wrong, but magnificently, spectacularly, completely wrong. And time, oh, time is the greatest example of this there has ever been. Let me start simple. You wake up in the morning, you make yourself some coffee, you drink it, then the cup is empty. That happened in a specific order. Coffee in the cup, then coffee in your stomach. You would never wake up and find your stomach full of coffee that then jumped back into the cup. Never. That only goes one way. You drop an egg on the floor. It shatters. You never, ever walk into a kitchen and see 1,000 pieces of eggshell spontaneously leap up from the floor, assembling themselves back into a perfect egg, which then flies upward into your hand. Never. That only goes one way. You are born, you age, you die. Only one direction, always forward. The universe, it seems, has a very clear preference for which way time goes. Past to future, always, without exception. So here is my question to you. And I want you to really think about this, because it is one of the most beautiful questions in all of physics. Why? Why does time only go one way? Is there something in the fundamental laws of physics, in Newton's equations, in Maxwell's equations, in Schrödinger's equation, in Einstein's field equations, is there something in there that says forward only? Some arrow built into the machinery of reality that points from past to future and refuses to point any other way? And this is where it gets spectacular, because the answer, the honest, experimentally verified, mathematically rigorous answer is no. There is no such arrow in the fundamental laws of physics. None whatsoever. The laws of physics, at their most basic level, work exactly the same going forward in time as they do going backward in time. Let me say that again, because I want it to sink in. The laws of physics, the rules that govern how every particle in the universe moves, interacts, collides, and behaves, those laws are perfectly symmetric in time. Run them forward, run them backward, they give you the same results. The universe, at its fundamental level, doesn't know which way time is supposed to go. It doesn't care. It can't even tell the difference. This property has a name. Physicists call it T-symmetry, T for time. Symmetry because the laws look the same when you replace T with negative T when you run the clock backward. And this isn't a guess. This isn't a hypothesis. This isn't something we think might be true. This is something we have tested over and over and over again with extraordinary precision, and it holds up. The laws of physics are time symmetric. They work the same in both directions. Now let me show you exactly what I mean, because I don't want you to just take my word for it. That's not how we do things in physics. We show our work. Take the simplest possible example. Newton's laws of motion. You've heard of them, I'm sure. F equals ma. Force equals mass times acceleration. A billiard ball rolls across a table and hits another billiard ball. The second ball goes flying off. Now, take a video of that. Play it forward, ball 1 hits ball 2 moves. Play it backward, ball 2 moves back, ball 1 moves back. Can you tell which version is the real one just by watching? No, you cannot. Both versions are perfectly consistent with Newton's laws. Both are physically valid. Both could actually happen. This is remarkable. The most basic equation of motion in classical physics has no preferred direction in time. Play the movie forward or backward, and Newton says both are fine. What about gravity? Einstein's general theory of relativity, the most precise and beautiful theory of gravity we have ever developed, does it have a preferred direction of time built into it? No. Einstein's field equations are perfectly time-symmetric. You can take any solution to those equations, run time backward, and get another perfectly valid solution. Planets can orbit stars going either direction in time, according to Einstein. Black holes can form or unform, again, mathematically. Both are valid. Electromagnetism, Maxwell's equations, which describe how electric and magnetic fields behave, how light moves, how radio waves travel. Time-symmetric. Run them backward and you get what physicists call advanced waves instead of retarded waves, waves that travel backward in time to their source insteadward to their destination. Mathematically completely valid. The equations allow it. Quantum mechanics, Schrodinger's equation, which tells us how quantum systems evolve, time-symmetric. The equation works perfectly well going backward. If you know the quantum state of a system right now, you can evolve it forward in time to find its future state, or you can evolve it backward in time to find its past state. The mathematics treats both directions identical. Are you starting to see the problem? Every fundamental equation we use to describe reality, every law we have discovered about how the universe actually works at its deepest level, every single one of them is blind to the direction of time. They work just as well going backward as going forward. They do not in any way contain an arrow of time. So where does the arrow come from? Why does your life only go one direction? Why can you remember yesterday but not tomorrow? Why do broken eggs never reassemble? Why does coffee never unpour itself back into the pot? That's what we're going to explore. And I promise you, by the time we're done, your head is going to be spinning in the most delightful way possible. Because the answer is stranger, more subtle, and more mind-bending than you could possibly imagine. But before we get there, I want to make absolutely sure you feel the full weight of what I've just told you. Because I think people hear the laws of physics are time-symmetric, and they nod along, but they don't really feel it. They don't really let it land. So here is a thought experiment. Imagine I have a camera. I film a single helium atom bouncing around inside a box. Just one atom. It hits the wall, bounces back, moves across the box, hits another wall, bounces again. Now I take that footage and I show it to you. I ask you, is this film playing forward or backward? What would you say? You'd have absolutely no idea. There is no way to tell because a single atom bouncing around looks exactly the same going forward in time as going backward. The physics is identical in both directions. Now here's where it gets interesting. What if I showed you a film of 1 billion atoms, a cup of coffee, cooling down? The atoms slow down, the temperature drops, the coffee loses heat to the surrounding air. Can you tell if I'm playing that forward or backward? Absolutely yes. You know perfectly well that the film going forward shows the coffee getting cold. If I play it backward, you'd see the coffee spontaneously getting hot, pulling heat in from the cool surrounding air, getting hotter and hotter on its own. You'd know immediately that something was wrong with the film. One atom, no arrow of time visible. 1 billion atoms, the arrow of time is crystal clear. This tells us something profound. The arrow of time is not a property of individual particles or individual physical laws. It is an emergent property, something that appears when you have large numbers of particles together, but is invisible when you look at the tiny, fundamental, particle-by-particle level. The universe's timekeeping is not written in its laws. It's written somewhere else entirely. And finding out where, now that is the adventure we are about to go on. The Feynman trick, when antimatter is just matter going backward. Now I want to tell you about one of the strangest and most beautiful ideas that I personally had a hand in developing. Not because I want to brag well, maybe a little, but because it perfectly illustrates just how seriously physics takes this whole time can go either direction business. And it involves antimatter, real antimatter, the stuff that sounds like science fiction but is absolutely, experimentally, demonstrably real. Let's go back to the 1940s. World War II had just ended. There was a whole generation of young, brilliant, excited physicists who wanted to figure out how quantum mechanics and special relativity could be combined into a single theory. How do the rules of the very small quantum mechanics combine with the rules of the very fast Einstein's relativity? This was one of the great open problems of the day. And in the process of figuring this out, something remarkable kept happening. The mathematics kept insisting, kept absolutely demanding that for every particle that exists, there must be a corresponding antiparticle. The electron has the positron. The proton has the antiproton. For every particle, an antimatter twin, identical in mass but opposite in charge, and other quantum properties. This seemed bizarre. Why would the mathematics require the existence of particles that nobody had ever seen? But we looked for them, and we found them. Antimatter is real. We create it in particle accelerators. We use it in PET scans and hospitals. Antimatter exists. But here is what I find absolutely magnificent about antimatter, and this is the idea that I played with, that I turned into something beautiful. What is an antiparticle, really? What does it mean, at the deepest level, for a particle to be its own antimatter twin? Here is my answer. And I say this with full seriousness and full physics behind it. An antiparticle is a regular particle moving backward in time. An anti-electron, a positron, is just an electron that, instead of moving from the past to the future, is moving from the future to the past. A positron is an electron going backward through time. I know what you're thinking. You're thinking, Feynman, come on, that's a cute metaphor. But surely you don't mean it literally. And I say to you, I absolutely mean it literally. This is not a metaphor. This is not a convenient fiction. This is a real, mathematically precise, experimentally verified statement about the nature of reality. Let me show you. When I developed what are now called Feynman diagrams, little pictures you can draw to calculate what happens when subatomic particles interact, I discovered something remarkable. You can take any diagram where a particle moves forward in time, and you can simply flip the direction of time for that particle, run it backward, and what you get is a diagram for the corresponding antiparticle doing the opposite interaction. Particle going forward in time and particle going backward in time are the same thing, described from different perspectives. This isn't just a clever trick. This mathematical equivalence has real physical consequences. It predicts the right masses for antiparticles. It predicts the right charges. It predicts how antiparticles interact with electromagnetic fields. Everything checks out. The mathematics of antiparticles going backward in time gives you the correct physics. There's even a story I love to tell about this. John Wheeler, my great mentor and teacher, a man whose mind worked in ways that continued to astonish me, he called me up one day when I was a graduate student. He said, Feynman, I think I know why all electrons have exactly the same charge and exactly the same mass. I said, why, Professor Wheeler? He said, because they're all the same electron. His idea was this. Imagine a single electron that zigzags through all of time. It goes forward in time for a while, then turns around and goes backward in time, then turns around and goes forward again, and so on a cosmic zigzag through all of history. When the electron is going forward in time, you see it as an electron. When it's going backward in time, you see it as a positron. This one electron, snaking its way through time in both directions, appears at any given moment as billions upon billions of particles, all electrons when moving forward, all positrons when moving backward, all with exactly the same mass and charge because they are literally the same particle. Wheeler called this the one-electron universe. It's not the mainstream accepted picture today. It has some problems I won't bore you with right now, but the point of it, the beautiful point, is that physicists think about particles traveling in both directions through time with complete seriousness. This is not science fiction. This is the working vocabulary of theoretical physics. Now, there is one place in physics where time symmetry seems to break down, and I must be honest with you about this, because I believe in being absolutely honest, even when it complicates my beautiful story. There is a class of particles called kaons, K-mesons, and also B-mesons, and when you study how they decay, you see something subtle. The laws governing their decay are not perfectly time symmetric. If you run the decay process backward, you don't get the same result. There is a genuine, measurable, real asymmetry in time built into the physics of these particular particles. This is called CP violation, or equivalently, by a theorem called the CPT theorem. This means T violation, time violation, a genuine physical process that actually distinguishes between forward and backward time. This seems like a devastating problem for my beautiful story about time-symmetric physics, but here is the twist. The effect is incredibly small, unimaginably tiny, microscopic. It is nowhere near large enough to explain why you can remember your childhood but not your future. It is nowhere near large enough to explain why broken eggs don't reassemble. This tiny T-violation in exotic particle decays is real, but it cannot be the source of the arrow of time as we experience it in everyday life. The arrow of time, you feel the one that's making you get older right now, the one that made your coffee go cold this morning, the one that turned a beautiful, alive human being you once loved into someone who is no longer here. That arrow of time has absolutely nothing to do with kaon decays. It comes from somewhere else, somewhere much more fascinating. And speaking of fascinating, I want to take a moment here and talk about something that I think captures the strangeness of all this better than any equation I could write. It's the question of memory. Why can you remember the past but not the future? This seems obvious, right? You remember the past because it already happened. The future hasn't happened yet, so there's nothing to remember. Simple. But wait. If the laws of physics are time symmetric, if the universe's rules work the same going forward and backward, then why should already happen be any different from hasn't happened yet? If the physics doesn't distinguish between past and future, why does your brain? Because a memory is a physical thing. When you remember your first day of school, that memory is stored in physical structures, in your brain, in the arrangement of proteins, in the connections between neurons, in patterns of electrochemical signals. Those physical structures exist because of physical processes. And physical processes are governed by the laws of physics. And the laws of physics are time symmetric. So why do those physical structures only record the past and not the future? Why can information about past events get encoded in your brain, but information about future events cannot? This is a real question, a deep question. And the answer to it points toward the real source of time's arrow, the thing that actually breaks the symmetry and gives time its direction. We're going to get there, I promise. But first, I want to talk about entropy, the most misunderstood concept in all of physics, because entropy is the key that unlocks this whole mystery. Entropy is where the arrow of time actually lives. Entropy, the one thing in the universe that knows which way is forward. There is a law of physics that is different from all the others. Most laws of physics are exact, precise. They tell you exactly what will happen. Newton tells you exactly where the cannonball will land. Maxwell tells you exactly how fast light will travel. Einstein tells you exactly how much a mass will curve space-time. These laws are crisp, sharp, and deterministic. But there is one law, the second law of thermodynamics, that is fundamentally different. It doesn't tell you what will happen. It tells you what is overwhelmingly likely to happen. It's a law built not on mathematical necessity, but on probability, on sheer, overwhelming, stupefying probability. And it is this law, this strange, probabilistic, statistical law that is responsible for everything you experience as the flow of time. Let me tell you about entropy. But I want to tell you about it correctly, because most people, even most people who've taken physics classes, have a deeply confused idea of what entropy actually is. Entropy is usually described as disorder. You've probably heard this. High entropy means more disorder. Low entropy means more order. The second law says entropy always increases. Things always become more disordered over time. This is true, but it's a terrible way to explain why entropy increases and why it's connected to time. So let me give you a better picture. Forget disorder. Instead, think about this. Entropy is a measure of how many ways a system can be arranged while still looking the same from the outside. Let me give you a concrete example. Imagine I have a box divided into two halves. On the left side, I have 100 air molecules. On the right side, I have nothing, a vacuum. Now I remove the divider. What happens? The molecules spread out. They fill the whole box. Some molecules go left, some go right. They bounce around, and very quickly you have molecules spread roughly evenly throughout the entire box. The gas expands to fill the space. You've seen this a million times. Now here's my question. Why don't all 100 molecules spontaneously decide to all jump back to the left half of the box? Why doesn't the gas unexpand? The physics allows it. Newton's laws say each individual molecule could reverse its velocity and retrace its path. So why doesn't it happen? Here's why. Imagine each molecule can be on either the left side or the right side of the box. That gives two possibilities per molecule. With 100 molecules, the total number of possible arrangements is 2 to the power of 100. That's a number with 30 zeros in it, an incomprehensibly huge number. Now, how many of those arrangements have all 100 molecules on the left side? Just one. There is exactly one arrangement where every single molecule happens to be on the left side of the box. So the probability of all molecules being on the left side is 1 inch to 100. That's a probability of approximately 1 inch 10 followed by 30 zeros. For practical purposes, impossible. You would have to wait longer than the age of the universe, much, much, much longer to have a reasonable chance of seeing that happen by random chance. This is entropy. The disordered state molecules spread throughout the box has an astronomically larger number of possible arrangements. So if you start from any random arrangement and you wait, you will almost certainly end up in a disordered state simply because there are so many more of them. It's not a law in the sense that some force is pushing the molecules to spread out. It's a law in the sense that there are just many more spread out arrangements than concentrated ones, that the system will wander into a spread out arrangement almost immediately and essentially never wander back. That is entropy. That is the second law. And now I can tell you with precision where the arrow of time comes from. The arrow of time comes from the fact that the early universe started in an extraordinarily low entropy state, an incredibly special, improbably concentrated, unimaginably ordered configuration, and has been evolving toward higher and higher entropy ever since. The Big Bang didn't just create space and time and matter. It created a universe in an almost impossibly special initial condition, a state of incredibly low entropy. And because the second law is what it is, because high entropy states vastly outnumber low entropy states, the universe has been moving from that special low entropy starting point toward ever more numerous, ever more disordered configurations. That's the arrow of time. That's why your coffee gets cold and not hot. That's why eggs break and don't unbreak. That's why you grow old and don't grow young. But now, and this is where I want you to really pay attention, notice what I've done. I've explained the arrow of time, yes, but I've explained it as a statistical effect, a probabilistic phenomenon, not as something written into the fundamental laws of physics. The fundamental laws of physics are still time symmetric. They still don't care which way time goes. What's broken, the symmetry, is not a law, but a boundary condition, the special low entropy state of the early universe. If the universe had started in a high entropy state, if the Big Bang had produced a uniformly spread out, featureless soup, there would be no arrow of time. Time would be symmetric in both directions. Nothing would be any more likely to go forward than backward. This is the deep answer to the mystery of time's direction. It's not in the laws, it's in the initial conditions. But this raises an even deeper question, and I warn you, this one is going to make your head hurt in the best possible way. Why did the universe start in such an incredibly low entropy state? What are the odds of that? The physicist Roger Penrose has made a famous calculation. He estimated the probability that the universe would start in the low entropy state required to produce the arrow of time we observe. The answer he got was staggering. The probability was 1 inch 10 to the power of 10 to the power of 123. That's not a typo. 10 to the power of 10 to the power of 123. This is a number so monstrously large that if you wrote it out, if you tried to write all its digits, you could not fit them in the observable universe. The universe's low entropy starting point was, statistically speaking, one of the most special, one of the most improbable configurations that could possibly exist. And yet here we are. Why? We don't know. This is one of the genuinely open, genuinely deep, genuinely unsolved problems in physics. Why did the universe start at such low entropy? Some people appeal to inflation, the rapid expansion in the first moments after the Big Bang. Some people appeal to the anthropic principle. We can only exist in a universe with an arrow of time. So of course we observe one. Some people think the answer lies in quantum cosmology, in the wave function of the universe itself. Nobody really knows, and I find that absolutely wonderful. But here's the thing I want to leave you with at the end of this section. Remember how I started, how the fundamental laws of physics are time symmetric? Remember how there's no arrow built into Newton or Einstein or Schrödinger or Maxwell? Remember how the universe, at its deepest level, doesn't know which way time goes. Everything you experience is the arrow of time. Every memory, every aging cell in your body, every cup of coffee that goes cold, every moment of grief for something lost, all of it traces back not to any fundamental law, but to one extraordinary, improbable, almost impossibly special fact. The universe began in a state of extraordinarily low entropy. Everything else follows from that. Take away that special initial condition, and there is no arrow of time. Time would run both ways equally well. The direction of time is not written into the laws of the universe. It is a historical accident, a consequence of how things happen to start. A scar if you want to think of it that way, left on the universe by its own birth. I find that remarkable. I find that astounding. And I find it deeply humbling, because it means that the most obvious feature of your entire existence, the fact that time goes forward and not backward, is not inevitable. It's not necessary. It's not fundamental. It's a peculiarity of the particular universe you happen to have been born into. The block universe, time doesn't flow, you're just moving through it. All right, we've established that the fundamental laws of physics are time symmetric. We've established that the arrow of time is a statistical effect, a consequence of entropy and the low entropy beginning of the universe, not a fundamental feature of reality. Now I want to take you somewhere even stranger. I want to talk about what time actually is. Because here's the thing. When I say time flows forward, what do I actually mean? What is this flowing? What is this sense of the present moment moving, of now constantly advancing from the past into the future? Einstein, my great predecessor, the man whose work I spent much of my career building upon Einstein, gave us a picture of reality that most people have heard of, but very few have truly absorbed. Relativity. And what relativity tells us about time is this. Time is not a universal, absolute thing that flows at the same rate for everyone. Time is a dimension, the fourth dimension, woven together with the three dimensions of space into a single four-dimensional fabric called space-time. In Einstein's picture, the universe is not a three-dimensional place that changes over time. It is a four-dimensional structure, a four-dimensional block, in which all moments of time, past, present, and future, exist simultaneously. Everything that has ever happened, everything that is happening now, everything that will ever happen, all of it exists right now in this four-dimensional block. It all just sits there, laid out, fixed, eternal. This view of reality has a name. Physicists and philosophers call it the block universe, or eternalism. And it is the picture of time that is most naturally consistent with Einstein's relativity. Let me explain why. In Newtonian physics, there is an absolute now. Everyone in the universe shares the same present moment. The concept of simultaneity, two things happening at the same time, is universal. If two events happen simultaneously for me, they happen simultaneously for you, regardless of how you're moving. Einstein showed that this is wrong. In special relativity, simultaneity is relative. Two events that happen at the same time for one observer happen at different times for another observer, moving relative to the first. There is no universal now. There is no absolute present moment that all observers share. Different observers, moving at different speeds, will disagree about which events are now and which events are in the past or future. This has a radical implication. If your now and my now are different, if events that are in your future are already in my past, depending on our relative motion, then what does it mean for time to flow? Flow toward what? Flow for whom? If the present moment is different for every observer, there is no single flowing present that all of reality shares. The natural resolution, the one that relativity most strongly suggests, is that all moments of time simply exist. The past exists, the present exists, the future exists. They all exist equally, laid out in the four-dimensional block of space-time. What you call the present is just your current location in this four-dimensional block. What you call time flowing is really just your consciousness moving along, your world line, your path through space-time, from your birth to your death. Time isn't flowing, you are moving through it. This is a profound shift in perspective. Think about space for a moment. Right now, you exist at a particular location in space, wherever you're sitting or standing right now. But that doesn't mean other locations in space don't exist. New York exists even if you're not there. Tokyo exists. The moon exists. These places exist even though you're not currently at them. The block universe says the same is true of time. Yesterday exists, it's just a location in space-time that you've already moved through. Next Tuesday exists, it's a location in space-time that you haven't reached yet. Your birth exists. Your death exists. They're all just different addresses in the four-dimensional block. I know this is deeply uncomfortable. It feels wrong. It feels like it can't be right, because you feel the present moment moving. You feel the future becoming the present and the present becoming the past. You feel time passing. How can that be an illusion? Here's a careful answer. Your experience of the present moment is real. Your consciousness, whatever consciousness is, seems to be localized to a particular moment. You don't simultaneously experience your birth and your death and your fifth birthday. You experience one moment at a time, sequentially. And that sequential experience feels like time flowing. But here's the question. Does the universe flow? Does reality itself flow? Or is it just your experience that has this sequential, one moment at a time character? Relativity says reality doesn't flow. The block exists. All of time is laid out. Your experience is sequential because of the nature of consciousness, because of the way your nervous system works, because of entropy and the arrow of time we discussed earlier. But the underlying reality, space-time itself, is static, eternal, fixed. Now, there's a beautiful and strange consequence of this view that I want you to sit with. If the block universe is correct, if past, present, and future all equally exist, then in what sense do things change? In what sense does anything happen? In the block universe, nothing changes, nothing happens. Events don't occur, they simply are. Your birth simply is at a certain location in space-time. Your death simply is at another location in space-time. The falling of the egg simply is. The cooling of the coffee simply is. These are not events that happen. They are features of the static block, no different from the way the mountains of Colorado simply are located at particular positions in space. Change in the block universe is just the difference between different locations in space-time. Things change over time is just a way of saying things are different at different positions along the time dimension. The same way things vary across space is a way of saying things are different at different positions along the space dimensions. Neither one involves actual change, just variation across a static structure. This view is deeply philosophically significant. It has implications for free will. If your future already exists, fixed, immutable, laid out in the four-dimensional block, then in what sense do you have choices? In what sense do you make decisions? This is a question that philosophers and physicists argue about endlessly, and I won't pretend there's an easy answer. But I want you to feel the question. Now, let me be honest with you, as I always try to be. The block universe is not the only interpretation of what relativity implies about time. There are physicists and philosophers who resist it. Some argue for a growing block universe, where the past and present exist but the future does not, where reality is being created moment by moment as time advances. Others argue for what they call presentism, the view that only the present moment is real, that the past no longer exists and the future doesn't exist yet. These views have their own problems. They're in serious tension with special relativity, which, as I said, undermines the notion of a universal present moment. But smart people hold them. The nature of time is one of those areas in physics where there is genuine, unresolved, deep disagreement. What I can tell you is this. The picture of time that is most naturally consistent with our best physical theory, Einstein's relativity, is the block universe. The picture in which time does not flow. The picture in which all of time simply exists, laid out. And what you experience as the passage of time is your consciousness moving along your world line through the static four-dimensional block of space-time. And here is the thing that gets me, the thing that I find most beautiful and most disorienting about all of this. You are not moving forward in time. From the perspective of the block universe, from the perspective of the four-dimensional reality that physics describes, you don't move at all. You simply exist all at once, stretched from your birth to your death, a four-dimensional worm in the four-dimensional block of space-time. The sense of movement, of flow, of the present rushing forward, that's something happening in your consciousness, in your experience, not in the external physical universe. The universe is still. You are the one who thinks it moves. Quantum mechanics and the arrow of time, where it gets really weird. Now we come to the part that even physicists argue about. The part where the foundations of our most successful scientific theory, quantum mechanics, run headlong into the question of time's arrow. The part where things get genuinely, deeply, philosophically unresolved. The part I love most of all. Quantum mechanics is strange. You heard this. Everyone says quantum mechanics is strange. And they're right, but not always for the right reasons. Quantum mechanics isn't strange because it's complicated, or because particles are small, or because the math is hard. Quantum mechanics is strange because it seems to be telling us something deeply unusual about the nature of reality, something that we don't fully understand. Even today, even after nearly 100 years of using quantum mechanics to make the most precise and accurate predictions in the history of science. Here is the central issue. In quantum mechanics, Before you measure a particle, before you interact with it, before you observe it, the particle exists in what we call a superposition. It doesn't have a definite position, or definite momentum, or definite spin. It exists in a kind of smeared out, indefinite state, a wave function that spreads through space, encoding probabilities for what you might find when you eventually look. And this wave function evolves according to Schrödinger's equation, beautifully, precisely, reversibly, time-symmetrically. Run Schrödinger's equation forward, and you can predict the future state of the wave function. Run it backward, and you can reconstruct the past state of the wave function. There's no arrow of time in Schrödinger's equation. It's time-symmetric, like everything else. But then, and here's where it gets strange, you measure the particle, you observe it, and something happens that Schrödinger's equation does not describe. The wave function collapses. The particle, which had been spread out in a superposition of many possible states, suddenly takes on a definite state. It's here, not there. It's spin up, not spin down. The indefinite becomes definite. And here is the key point for our discussion of time. This collapse of the wave function, this measurement process, is not time symmetric. If you run the measurement process backward, you don't get valid quantum mechanics. The collapse goes one way. It picks a definite state from the superposition, and it never goes back. Possibilities become actualities, and that process is one-directional. This is the infamous measurement problem of quantum mechanics. What is measurement? What causes wave function collapse? Is collapse a real physical process, or is it something else? Physicists have been arguing about this for 90 years, and the argument is not over. There is genuinely no consensus. But for our purposes, for the question of time's arrow, here is what's significant. Wave function collapse, whatever it is, looks like it might be a source of time's arrow at the quantum level. The quantum world, before measurement, is time symmetric. After measurement, after collapse, definite facts are established that cannot be undone. That looks like an arrow of time. But wait, does wave function collapse actually happen? Not everyone thinks so. There is an interpretation of quantum mechanics, and it's a serious, scientifically mainstream interpretation, not a fringe idea called the many worlds interpretation. It was developed by Hugh Everett in the 1950s, and it says, wave functions never collapse, ever. Schrödinger's equation always applies to everything, including measurement devices, including physicists, including everything. What happens when you measure a particle in the many worlds interpretation? The universe, the entire wave function of the universe, branches. When you measure a spin-up, spin-down particle, the universe splits into a branch where you measured spin-up and a branch where you measured spin-down. Both branches are equally real. Both versions of you exist, each in their own branch of the universal wave function. You just happen to be in one of them and not the other. In the many worlds interpretation, Schrödinger's equation always holds. Wave functions never collapse. The evolution of the universe is always governed by a time-symmetric equation. And so the many worlds interpretation has a problem. It needs to explain where the arrow of time comes from without wave function collapse. And the answer it gives? Entropy. The branching of the wave function into more and more branches, the spreading of quantum superpositions into more and more worlds, is essentially a quantum version of entropy increase. The number of branches grows monotonically. You can branch, but you can't unbranch. And this monotonic growth of branches plays the role of the arrow of time. We're back to entropy, always entropy. Now, there is another approach to quantum mechanics and time that I find deeply beautiful, and it's one that connects back to things I worked on personally. It's called the path integral formulation of quantum mechanics, and it's a way of thinking about quantum mechanics that treats time in a very different way. In ordinary quantum mechanics, you start with a particle at some position, at some time, and you calculate how the wave function evolves forward to the next moment, then the next, then the next. Time marches forward, step by step. In the path integral formulation, you think about it differently. You say, a particle gets from point A at time t1 to point B at time t2. What is the probability of this? And the answer is, you consider every possible path the particle could have taken from A to B, every path through space, no matter how wild, no matter how physically absurd looking, and you add up the contributions of all these paths. The particle somehow samples every possible path simultaneously. And the most probable paths are the ones where these contributions reinforce each other. Quantum mechanics emerges from this sum over all possibilities. What's beautiful about this from the perspective of time is that the path integral treats the beginning and end of the journey symmetrically. You specify the starting point and the ending point, and then you sum over all paths connecting them. Past and future play equal roles. The computation doesn't have a preferred direction. Time's arrow doesn't appear. It's not in the formalism. There's an even stranger version of this idea developed by Yakir Aharonov and colleagues, the two-state vector formalism. In this approach, the quantum state of a system is not just determined by measurements in its past. It's jointly determined by measurements in its past and measurements in its future. The quantum state of a particle right now depends on what will happen to it in the future, not just on what has happened in the past. This is called post-selection in quantum mechanics. And it's not just theoretical. There are real experiments in quantum mechanics where the results can be better understood by considering both past and future boundary conditions. The future genuinely influences the present in a way that's experimentally testable. Does this mean your future is influencing your present right now? In the quantum mechanical sense, possibly yes. The universe might be running both forward and backward in time simultaneously, with the past and future both serving as boundary conditions that jointly determine the present. I want to be careful here. I don't want to overclaim. These are interpretations, not settled physics. The two-state vector formalism is not the accepted mainstream picture. The many worlds interpretation is not universally accepted. The measurement problem is genuinely unsolved. But here's the point I want you to take away. The arrow of time is not obvious or automatic, even in quantum mechanics, the most successful physical theory we have ever developed. In quantum mechanics, you have to work to get an arrow of time. You have to add something, whether it's wave function collapse or decoherence or the entropy of branching to recover the directed one-way time of everyday experience. The theory itself, Schrödinger's equation, is perfectly happy to run in either direction. And there is a final thing about quantum mechanics and time that I must tell you, because it is astonishing, and because I think it's one of the most important and underappreciated discoveries in modern physics. It's called decoherence. When a quantum system, a particle in a superposition, interacts with its environment, with the billions and billions of particles of air and light and other matter that surround it, the quantum superposition doesn't collapse dramatically all at once. Instead, the superposition leaks, slowly at first and then overwhelmingly fast, into the environment. The quantum correlations spread out into the environment. The superposition effectively disappears for any practical purpose because it's now entangled with the entire environment, and no measurement you could perform on the particle alone could detect the interference effects that characterize a superposition. This process decoherence is one-directional. Once the quantum coherence has leaked into the environment, you can't get it back. The quantum world becomes the classical world, irreversibly. And this irreversibility, this one-way transition from quantum to classical, is connected to entropy. Decoherence increases entropy. And decoherence happens in the forward direction of time, from low entropy to high entropy. So even in quantum mechanics, the arrow of time traces back, ultimately, to entropy, which traces back to the low entropy initial conditions of the universe, which is the deep, unresolved mystery we've been circling around this entire time. So what does it all mean? The mind-bending conclusion. We've come a long way together. Let me take a moment and remind you of the ground we've covered, because I want you to see the whole picture before I hit you with the final, most mind-bending implication of all of this. We started with a simple, obvious, seemingly undeniable fact. Time moves forward, past to present to future, always, without exception. You'd bet your life on it. Then I showed you that the fundamental laws of physics, Newton, Einstein, Maxwell, Schrödinger, are all completely, perfectly time-symmetric. They work identically, going forward and backward. There is no arrow of time built into the fundamental laws of the universe. The universe, at its deepest level, doesn't know which way time goes. Then I showed you that antiparticles can be understood as particles moving backward in time, that my own Feynman diagrams encode this explicitly, and that the mathematics of time-reverse particles gives you the correct physics of antimatter. Time reversal is not just an abstract symmetry. It's a real operation with real physical meaning. Then I told you about entropy, about how the enormous number of disordered states vastly outnumbers the number of ordered states, and how this statistical asymmetry creates an effective arrow of time. The second law of thermodynamics is not a fundamental law, but a statistical consequence of initial conditions. The arrow of time emerges from the extraordinarily special low entropy state in which the universe began. Then I told you about Einstein's block universe, the four-dimensional static structure of space-time, in which all moments of time, past, present, and future, exist simultaneously, in which time does not flow, in which you are a four-dimensional worm stretched from birth to death, and your sense of moving through time is something happening in your consciousness, not in the external physical universe. Then I told you about quantum mechanics, about how Schrödinger's equation is time symmetric, about how the arrow of time in quantum mechanics comes from decoherence and entropy, and about how interpretations like many worlds suggest a universe of branching wave functions where the past and future play symmetrical roles. Now, here is the question I want to end with. The question that, in my view, is the single most important question in all of this. The question that ties everything together and points towards something so strange and so beautiful that even after a lifetime of thinking about it, it still gives me a genuine chill. Why did the universe start in such a low entropy state? This is not a small question. This is not a technical detail. This is the question that everything else depends on. Without the low entropy beginning, there is no arrow of time. Without an arrow of time, there are no memories, no causation, no past or future, no sense of events happening in sequence. Everything you experience as real, your entire conscious life, every thought, every memory, every plan, is only possible because the universe began in a state of extraordinarily low entropy. But why did it? What determined the initial conditions of the universe? Why those initial conditions and not others? One approach is to appeal to the laws of physics themselves. Maybe the laws of physics, when you look at them quantum cosmologically, when you apply quantum mechanics to the universe as a whole, necessarily produce a low entropy beginning. Maybe there is something in the quantum wave function of the universe, something in the deep structure of quantum gravity that selects for low entropy initial conditions. Stephen Hawking and James Hartle developed what they called the no-boundary proposal, a picture of the quantum origin of the universe in which the concept of initial conditions dissolves and the low entropy of the early universe emerges naturally from the quantum geometry of space-time. This is beautiful and interesting, though not universally accepted. Another approach is inflation, the idea that in the very first moments after the Big Bang, the universe underwent a period of extraordinarily rapid exponential expansion which smoothed out any inhomogeneities and set up the initial conditions that led to the low entropy universe we observe. Inflation is the mainstream view, supported by observations of the cosmic microwave background, but it raises its own questions. What were the conditions before inflation? What started inflation? And does inflation actually explain the low entropy, or does it just push the problem back a step? A third approach is what some physicists call the multiverse, the idea that our universe is one of a huge, perhaps infinite number of universes, each with different initial conditions. In a multiverse with enough variety, some universes will happen to start in low entropy states, and in those universes, there will be observers like us who can ask questions like, why did our universe start in a low entropy state? In universes that started in high entropy states, there are no such observers because there's no arrow of time, and therefore no life, no evolution, no consciousness, no one to ask the question. We observe a low entropy beginning because we could not exist in a universe with any other kind of beginning. This is a version of the anthropic principle, and it makes many physicists deeply uncomfortable. It feels like it's not a real explanation. It feels like it's just saying, because if it were otherwise, we wouldn't be here to notice. But maybe that is the answer. Maybe the question of why the universe has the initial conditions it does is the same kind of question as why you were born to your particular parents in your particular town, not because of any deep law, but because of a combination of contingency, chance, and the simple fact that you couldn't be asking the question from any other starting point. I don't know which of these answers is correct. I genuinely don't know. And I want to be honest with you about that, because I think dishonesty in physics is a terrible thing. Anyone who tells you they know why the universe started in a low entropy state is either wrong or lying. It is an open question, one of the great open questions. But let me tell you what I do know, what I find most significant about this whole investigation. What, after thinking about it for decades, strikes me as the truly essential insight about time. The direction of time, the fact that your life goes from birth to death and not the other way. The fact that you can remember yesterday and not tomorrow. The fact that broken things don't fix themselves and dead things don't come back to life. This is not a fundamental feature of the laws of nature. It is a contingent feature of the particular universe we live in. It depends on the initial conditions. Change those initial conditions, and time might have no direction at all, or might have the opposite direction, or might have different directions in different regions. In a universe that started at maximum entropy, in a universe that had been running for infinite time in both directions from some central moment time, would have no overall arrow. There would be local fluctuations, local regions of low entropy, but no global sense in which forward is different from backward. The inhabitants of such a universe, if there were any, would have no concept of a direction of time. We have that concept because we won a kind of cosmic lottery, because we happen to live in a universe that started in an extraordinarily special, extraordinarily improbable state, because the Big Bang threw us onto the bottom of an entropic mountain, and we've been rolling downhill ever since. The downhill direction is what we call forward in time. There is something else I want to leave you with. Something that is not physics, but that I think follows from the physics. If the past and future both exist in the block universe, if tomorrow is as real and as permanent as yesterday, then what does that mean for how you think about loss? About the people and things and moments that are gone? In the block universe, they are not gone. They exist at their particular coordinates in space-time, as real and as present as anything that exists right now. The moment you held someone you loved who is no longer alive, that moment exists. It is there, in the block, permanent, real, as vivid and as full as it was when you lived it. It does not fade. It does not disappear. It exists at its address in space-time, and it will always exist there forever. I don't know if that's comforting. It might not be in the way you'd want it to be. It doesn't mean you can go back. It doesn't mean anything you might prefer it to mean in the conventional sense, but it means that the moments of your life, the beautiful ones, the ones you'd give anything to relive, they are real, they are permanent. The universe has not forgotten them, because the universe is not the kind of thing that forgets. The universe is a four-dimensional block, and every moment is preserved in it exactly as it was. Physics has given us a strange gift. By taking away the intuitive, flowing, forward-marching time we thought we understood, it has given us something stranger and, in a way, more beautiful. A universe in which every moment is eternal. A universe in which the past is not a category of things that are gone, but a category of things that exist at an earlier address. A universe in which the arrow of time is real in our experience, but not fundamental in nature, a beautiful, convincing, perfectly understandable illusion arising from entropy and initial conditions. Here's my final thought. The most important thing I know about the universe is this. It is far stranger than we imagine, and far stranger than we can imagine with our everyday intuitions. Every time we have listened carefully to what the mathematics is telling us, every time we have followed the equations, even when they led somewhere uncomfortable and counterintuitive, we have discovered something more beautiful and more astonishing than anything we would have guessed. Time is no exception. The physics of time is telling us something we don't want to hear, that our most basic, most intimate experience of reality, the feeling of moving through time, of living in a flowing present, is not what it seems. It's not fundamental. It's emergent. It's statistical. It's a consequence of history, specifically, of the particular history of the universe we happen to inhabit. And I say, isn't that wonderful? Isn't that the most astonishing thing? That this feeling so intimate, so undeniable, so absolutely central to what it means to be alive and conscious and present in the world, this feeling is woven from entropy and statistics and the quantum mechanics of a universe that began in an improbably special state. We are not passengers on a river being carried forward by the current of time. We are features of a four-dimensional block patterns in space-time with the extraordinary good fortune to be the kind of patterns that can ask why. The fact that we can ask why time goes forward, that we have the cognitive and linguistic and scientific tools to even formulate the question, is itself a consequence of the thing we're investigating. We can ask about time's arrow because we have memories. We have memories because we have brains. We have brains because of evolution. We have evolution because of the arrow of time, which exists because of entropy, which exists because of the low entropy beginning of the universe, which exists for reasons we don't yet understand. The circle closes, the mystery deepens. And that, my friends, is what makes physics the greatest adventure there has ever been.